Okay, guys, so we're talking about variables. So when you have an experiment, and I'm just talking about experiments here, case studies, surveys, and naturalistic observations do not have any variables that you manipulate. Only experiments do. And so for the next part of our notes, we're only talking about experiments, not the other types of research methods. So we have two types of variables. We have independent variables and dependent variables. And it's very important on the AP test that you can tell the difference between these two, that you can determine which one is independent and which one is the dependent, or you can make up your own independent and dependent variables. So an independent variable is anything that you're going to manipulate in the experiment. So let's say that you were doing, I remember doing this experiment in like third grade, where you have these little bean seeds and then you plant bean seeds in two different pots, and then you put one by the sunlight and then you put one in the closet, and you see which bean plant grows the most. Obviously the one that's getting the sunlight. But whatever is being manipulated in this experiment, in that experiment, it was the sunlight, whether or not the plant was getting sun or not. And so you're manipulating the amount of sunlight that they have. For psychology experiments, a lot of them are going to be dealing with like medicine. Give this group 10 milligrams of Ritalin, and then again this group, a placebo or something like that. And so hopefully the independent variable brings about change. If you're trying to see, what type of drug helps with ADHD or helps with depression, hopefully the drug is going to help with ADHD or depression, whatever you're trying to experiment. And so typically if you see an experiment and it uses a drug, the drug is the independent variable. It could also be different things. So let's say that I wanted to test whether, cold in a classroom increases test scores. And so I'm going to have one classroom be regular temperature, and then one classroom I'm going to crank up the air. And so it's going to be colder. I'm manipulating the temperature of the room. And so that's the independent variables, whatever you are changing. The dependent variable is the result. Their test scores, how high the bean plant actually did grow. It's whatever is being measured. It's the result of the independent variable. It is dependent on the independent variable. The height of the plant is dependent on how much sunlight it had. The test scores is dependent on how cold the room was. It is the result, is what you're measuring after the fact. So if you're measuring some sort of like drug and how that changes sleep patterns, the drug itself is the independent variable. How it changes your sleep patterns, the amount of sleep you got or how awake you are, that's the dependent variable. Okay, there are also other variables. Those are the main two, the independent and the dependent, but you also want to be aware of something called a confounding variable. So let's say that the object of the experiment is to prove that A causes B. A confounding variable is anything that would cause B that's not A. So let's say that you're trying to prove that smoking causes cancer, and experiments have already done that. But a confounding variable is anything that might cause cancer that's not necessarily smoking, and that could be lifestyle. That could be maybe it runs in their family, so they have genetic characteristics that would lead them to be have more cancer or something to that effect. Okay, so here's the experiment. If you want to prove that smoking causes heart issues, what are some confounding variables? It's anything that would cause heart issues that's not smoking. Bad diet, poor exercise, genetic predisposition, stuff like that. Okay, so how do you get rid of confounding variables? Because in every experiment, there's going to be some amount of confounding variables. How you want to get rid of it is by having sampling and random assignment. So first you have to identify the population you want to study. So let's say you want to study all of Tomo High School students. Well, that is your population.
Good morning, teachers. Hope everybody's having a great.
Okay, I'm back. So you first want to have a population. The population is the people that you want to study. And so, like, if you want to study the entire world, then your population is the entire world. But if you're really only trying to test, children from the ages of 7 to 17, then that's your population. Or if you want to just do adults that smoke, then that's going to be your population. And then you are not going to test everyone in the population, because that would just be crazy, to have an experiment where every single person of Tomball High School participates in. It would be too expensive. It would take too long. It's just too much of a hassle. So you're just going to get a sample of the population. And so you have to have a random sample. A random sample would not be passing out flyers to everyone in the hallway during passing periods, because number one, not everyone has an equal opportunity to be in the sample. Because what if you're not in the hallway during that passing period? What if you're running late? What if you're absent that day? What if you don't take that hallway? Not everyone has an equal chance, and that's what it means for it to be random. Everyone has an equal chance to be selected as part of the sample. So you got to get a random sample. And you have to have a stratified sample, meaning, let's say the general population of Tomball High School is 4% male and then 46% female. Well, then your sample needs to have that exact same percentage of population. If you have a random sample and 90% of them are male, that's not very random. And it's not a very good representation of what Tomball High School actually is, because that's not the characteristics of the population of Tomball High School. Same thing, not just like male and female, but for maybe sexuality, if that's an issue, or race, religion, age, where you need to make sure that the sample is a representation of the population you're trying to experiment on. Okay. And then you take that sample. So let's say we have 3,000 people at Tomball High School, and you're going to have a sample of so the population is 3,000, and you want to have a sample of just 300. Okay, so now you have 300 sampling of the population, and that you randomly got. You picked ID numbers. You had a random shuffle or of ID numbers. You picked names out of a hat, something like that. And then you're going to take those 300 sample, and you're going to equally split them randomly, like heads or tails, randomly, odds and evens, something like that, into two groups, the experimental group and the control group. And so the AP test really needs you to know the difference between population, sample, experimental group, and control group, and how you get all those things randomly. And so the experimental group is the one that's getting the independent variable, the one that we just talked about, whether they're getting the drug. Are they the plant that's getting the sunlight? Are they the people that are getting the colder temperature rooms to take tests in? And then the control group, they're going to not get the independent variable. That's what makes the control. You're going to be comparing the results of the experimental group to the results of the control group. Control group didn't get anything, so it's like what you're basing all your information off of. So the experimental group, they get the independent variable, they get the drug, they get whatever you're manipulating. Both groups are going to have some sort of result. The test scores, the height of the plant, or whatever it is, the result of the drug. And you're going to be comparing the dependent variable between the experimental group and the control. Okay, so now we're going to talk about confounding variables. So remember, confounding variables is anything that might mess up your experiment, anything that might cause the dependent variable that's not the independent variable, something that would change the results of the experiment without being the thing that you're trying to get to change the results. So the Hawthorne effect is a type of confounding variable, and was named after an experiment done in the 1950s at the Hawthorne electric plant. So what they did, they tried to change the lighting in the electric plant to see if that would change the factory workers' productivity. So they had, they had an experimental group, they had a control group. The experimental group got a different lighting condition than the control group. The control group just got the regular lighting condition, but I believe that they dimmed the lights for the experimental group, and then they had the people that were in charge of the experiment. It was their bosses. They had them walk around with little clipboards measuring their performance, measuring their productivity, and amazingly, not really, amazingly, both the experimental group and the control group were more productive. It didn't matter whether the lights were dimmer or whether they were getting the actual light that they typically get on an everyday basis. Both experimental and control groups had a report of higher productivity. Why would that be the case? Why would they both be more productive as their bosses were walking around measuring their productivity? It's because their bosses were walking around measuring their productivity. And so just the fact that you are in an experiment changes the results. The fact of being in an experiment is a confounding variable within itself. When you know you're part of an experiment, your activity, your behavior, what you say might change. And so whether the lights were brighter or dimmer in the electric plant, productivity went up just because they were that is an exchange. That is a change of the dependent variable. That's not the independent variable. It didn't matter whether the lights were dimmer or brighter or the same. What mattered is that they were in the experiment themselves, and that's a confounding variable. That's called the Hawthorne effect. Other confounding variables is experimenter bias. If the experimenter knows who's getting the drug, the active ingredient drug, or the placebo, some sort of sugar pill that's not supposed to do anything, if the experimenter knows who's getting what, they might be a little bit more likely to treat people differently. Subconsciously, they don't know that they're doing it. But if I, know that this group is getting like the drug to cure cancer, and then this group is getting some sugar pill that's not going to do anything, I might ignore what they say. But the people that got the active ingredient, I might be like, hey, how you doing? I feel that you're going to do better today. Don't you feel better? And that, me treating them differently, would actually change the results. You might give people hope or take away hope just by the way of me treating them. So how do I get around that? It's not a conscious act, but how I get around that is a double-blind procedure, meaning neither the experimenter nor the people participating in the experiment know whether they are getting the independent variable or if they're getting some sort of placebo. They don't know if they are getting the active drug or some sort of sugar pill. Neither the people getting it nor the experimenter. So it is a double blind, meaning both the experimenter and the participants of the study are blind to what's actually happening. So there's not going to be any sort of bias one way or another. And we've said the word placebo before, but placebo is a non-active drug. It is, think of giving college students a non-alcoholic beer and then giving another group of college students a beer with alcohol in it and seeing how they interact. The people that got the non-alcoholic beer, that will be a placebo. If they were to start acting drunk, which studies have shown that if you are given college students, non-alcoholic beer, they will act drunk. That's the placebo effect. If you give someone a sugar pill and tell them to cure cancer, it's going to cure cancer, they might feel like they're getting better, even though they're not. And you know what? They might actually be getting better just because of a little bit of hope that they're getting better. That's the placebo effect. Another one is an order effect. The order in which you do the experiment might actually change the experiment, depending on what you're studying. So let's say that I have you memorize a list of words, and then I test your memory, and then I have you memorize a list of some similar words after doing exercise or something. I'm like trying to see if exercise increases your retention of vocabulary. And I have you, memorize a list of similar words. Well, just the fact that it's a similar words probably makes you retain that information a little bit more whether you were doing exercise or not. So if you had a list of like farm animals that you had to memorize, and then I tested you on those, and then I made you do some exercise, and then I tested you on maybe like zoo animals as opposed to completely not animals at all. I tested you on zoo animals. You might remember the zoo animals a little bit more than the farm animals, just because I put you in the order of things, made you remember just animals to begin with. So that's a confounding variable in itself. So we try to get rid of the order, change up the order that you do things, or the placebo effect. You got to watch out for that, or you make sure there's no experimental bias with a double-blind procedure. Okay, let's talk about the idea of correlation versus causation. So I'm now switching kind of gears. A correlation, I'm going to actually see how much time we got here. Okay. There's a huge difference between correlation and causation. An experiment can show causation. Smoking causes cancer. This causes that. One will lead to the other. That's a causation. That can only be proven with an experiment. You cannot prove causation with a naturalistic observation, with a survey, or with a case study. You cannot do it. Only with an experiment, and only after repeated experiments, doing the experiment over and over and over again and replicating it, can you say that there's a causation. And so typically most studies are going to give you correlation, because most studies are not experiments. Most studies are surveys or naturalistic observations or case studies. Only, very infrequently are there experiments that actually have the weight to have a causation. So correlation expresses a relationship between variables, does not show causation. So, like this little picture right here says, did the AVAs cause the U.S. housing bubble? And so you see the housing price index, which measures house prices going up, and the amount of AVAs that were born. And you kind of see that those go together. But that's not, they're correlated. They're happening at the same time, but that does not mean that one is causing the other. And so it's kind of a joke between is it correlation or causation. Here's another thing that are correlated together: ice cream sales and murders in Houston, Texas. They are positively correlated. The more sale of ice cream, there's also a higher homicide rate in Houston. But it is not a causation. Ice cream sales do not cause people to be murdered. So how does it happen? Okay, well, the things that are happening at the same time, that's how they're related. Ice cream sales peak when it's hot outside during the summer. Also, during the summer when it's hot outside, heat causes people to be more aggressive. And so the fact that it's hot causes murders to go up, but it also causes the sale of ice cream to go up. So those are happening at the same time, but that does not mean one is causing the other. They are correlated, but they are not causing each other. Okay, and I said this kind of a little bit earlier. I said positive correlation. Well, there's positive correlation, or there's no correlation, or there's a negative correlation. And so a positive correlation, or a positive relationship between two variables, means that they go in the same direction. If more of this leads to more of that, and less of this leads to less of that. And you can actually see this on a graph right here. This is what the green line that sloped upwards, that is a positive relationship. Whatever is on the X and Y axis are positively related. More studying leads to more good grades. Less of studying leads to less good grades. So they go in the same direction. They're directly related. A negative relationship still means that there's a relationship. It just means that there's a negative one, meaning more of one variable will lead to less of another. So like more alcohol will lead to less memory retention. Less alcohol will lead to more memory retention. That's a negative relationship. More of A leads to less of B, and less of A leads to more of B. So the variables are going in opposite directions. And you can show that with a negatively sloped line on a graph. Whatever's on the X and Y axis is going to be negatively related. And then if there is no relationship, like more or less of this does not affect any more of this or the other, that's just no relationship. And you see that as like a scatter plot on a graph. So there's this idea of a correlation coefficient. A statistical measure of the extent of which the two factors relate to one another. So how much is it positively correlated? How much is it negatively correlated? So the correlation coefficient is going to be some number between -1 and +1. -1 and +1. Negatives just means it's a negative relationship. Positives, it means it's a positive relationship. So a +1 would be a perfect positive relationship. -1 would be a perfect negative relationship. And then 0, if it's a 0, that means there's no relationship whatsoever. So the closest it is to either +1 or -1, the stronger that relation. The more this leads to this, the more that leads to this. The closer to 0, the more of its like chance, the more it's likely to chance. Like there's, the murders and ice cream sales, that they're positive related, but that's not a strong relationship. It's not like a +1. It's not even going to be like a 0.9. It's probably going to be like a 0.4. So it's 0.4. It's positive 0.4. So it's a positive relationship. It's not a strong one. It's closer to 0 than it is to 1. So the plus or minus indicates the relationship, positive or negative, and then how close it is to either 0 or 1, positive or negative, indicates the strength. The closer it is to 1 or -1, the stronger the relationship. The closer it is to 0, the weaker it is. Okay, so you could probably get an idea of what the relationship is based on the lines of these graphs. So this is a -1. It's basically a straight negative sloping line versus a +1. It's really, really not scattered at all. I mean, you can draw basically a straight line between these points. These are kind of, clumped together, but it's sloped upwards. So it's a positive number. It's just not 1. And these are kind of clumped together, but sloping downwards. So it's a -0.94 in this example. This is no relationship. It goes up, down. There's no relationship here. And this is more of a scatter point. Look how close that is to 0. That is not close to -1 or +1. That is close to 0. And so it's a scatter plot. Okay. And we just said this. The number that it measures the strength of the relationship, the range is -1 to +1, and the relationship gets closer to, is weaker the closer it gets to 0. Okay. You can ask yourself, which one of these is stronger, -0.13 or +0.38? So for strength, we're not looking at positive and negatives. We're looking at how close it is to either -1 for a negative relationship or +1 for a positive relationship. And so plus 0.38 is closer to 1 than -0.13 is closer to -1. So that's going to be the stronger one. For the next one down, we have -0.72 or +0.59. It's going to be -0.72 because it's closer to -1. And for the third one, we have -0.91 or +0.04. Definitely it's going to be the -0.91 because that's really close to -1, and then 0.04 is so close to 0 that it's barely even correlated at all. Okay, so that's where we're stopping today, and we will be practicing the idea versus, negative versus positive relationships and correlation coefficients in class. All right, thank you.